Hello everybody, and welcome back to example 1 on page 61 of the workbook. This is the continuation of an example that we started earlier. Let's just refresh our memory what was going on here. So this was about the population of a bacteria colony, kind of comes from this differential equation, and we talked before qualitatively about what this slope field is telling us. Okay, so the idea of what we did so far is that we took a couple of initial conditions and we drew in solution curves, but they were very approximate. They kind of told us, roughly speaking, how the population is increasing. What would be really nice is if we could find formulas for those curves. That would make calculations like what we did in part B more accurate. We had to really estimate what the doubling time of this population was. If we had a formula for those curves, we could be a lot more accurate in our estimates. Okay, that's kind of what part C is about here. It gives us the first step in that direction of being able to find a formula for a curve as a solution to a differential equation. Okay, let's read this together. So for each of the following functions, use the slope field to guess, first of all, whether the function could be a solution, and then to use algebra and calculus to confirm our guesses. Okay, so here's what I'm going to ask you first to get started on this. I want you to maybe pause the video at this point and to think about these four functions one at a time. Okay, think about what their shapes would be. You could even graph them on a graphing calculator, and here's the question that you want to ask. Ask yourself, once you have a graph of the function in front of you, does it look like it's a function that would fit into our slope field that we have here? Would its basic shape match the basic shape that's described by the slope field? Okay, and don't worry about being right or wrong here. I'm just asking you to make some guesses as to which of these might be solutions. Okay, welcome back, and hopefully you've made some guesses as to which of these four functions might actually be solutions to our differential equation that fit in the slope field here. What we want to talk about now is how we might confirm those guesses. Okay, to really convince ourselves which of these four functions down here are solutions. Okay, now this method that we're about to give is going to be quite different than what we've done up to this point in the course, so I want to offer you kind of an analogy from algebra that might help us to think about this. Okay, so I'm going to flip pages here on you. Okay, and just pose a question to you that you might see in an algebra class. And here's the question. Is the number y equals 2 a solution to the equation y to the fourth equals 6y plus 4? Okay, how would you answer that question? Okay, well, you may very well be able to do something like that in your head and come up with an answer of yes. Okay, but let's dig a little deeper here and think about how you might explain this to an algebra student who's new to this concept of what it means for something to be a solution. Okay, the basic idea is you want to take this y equals 2 and plug it into your equation and confirm that you get a true statement. And so if you really wanted to break it down into details, here's what you might do. You might start with the left-hand side of your equation. I'm going to abbreviate that LHS for left-hand side. The left-hand side of the equation is y to the fourth, and then you would take the thing that you want to check, the number 2, and you would substitute it in, okay, for the y. That would give you 2 to the fourth, which is 16. There's the value on the left-hand side of the equation, and you would compare that to the right-hand side of the equation, which looks like 6y plus 4. Okay, and you would ask, what do I get if I plug y equals 2 into the right-hand side? Well, let's see. You would get 6 times 2 plus 4. That's 12 plus 4, which is 16. And then notice, we get the same thing. 16 on both sides of the equation. That confirms that our equation is a true statement. Okay, so since the left-hand side and the right-hand side are equal, y equals 2 is a solution. Okay, now you might have been able to do that problem without writing as much as I did. You could maybe do that in your head, but we're going to use the same principle to check the solutions to our differential equation. Okay, so keep in mind that what we're about to do is very similar to what we just did on the previous page here. All right, so let's start with the equation p equals e to the 0.3t. Is that a solution to this differential equation? Well, to check that, we just need to substitute in e to the 0.3t to the left and the right-hand side of our differential equation and see if we get the same thing. All right, so number one, we are going to check p equals e to the 0.3, e to the 0.3t. Okay, and so we'll use the same approach that we did on the previous page. We'll look at the left-hand side and the right-hand side separately. The left-hand side of our differential equation looks like dp dt, and the right-hand side looks like 0.3p. And to check to see if this is a solution, we're going to take the value of p, which is e to the 0.3t, and we're just going to substitute it in to the left and the right-hand side. So if we substitute in for p on the left-hand side, that p is going to turn into an e to the 0.3t. And then the question is, what does it mean when we write d dt of e to the 0.3t? Well, that's really telling us take the derivative of e to the 0.3t. So what happens when we do that? Well, if you take the derivative of e to a power, you get the same thing back again. But the chain rule says we need to multiply by the derivative of the exponent. The derivative of 0.3 times t is 0.3, and so that's also part of our derivative. Okay, so we've completed the calculation for the left-hand side, and now we come to the right-hand side. And exact same idea, we want to take the value of p, which is sitting up here, and substitute it in for the p that we're seeing there. So I'll take that p and literally replace it with e to the 0.3t. And notice there's no derivative on the right-hand side. We're done with the calculation. It's just telling us to take 0.3 and multiply it by p. And my question to you is, did we get the same thing on the left and the right-hand side of the equation? We actually did. These two things are equal. And so we have confirmed that this formula, p equals e to the 0.3t, is a solution. Okay. So, I don't know what you guessed. I asked you to kind of take a guess as to whether you thought that this curve might be a solution. If you answered yes, you might have noticed that if you were to graph this function, it kind of has an increasing and concave up shape. It's an exponential function, and that type of a curve kind of fits into this slope field. So graphically, it seems plausible that that might work. Okay, so we have checked one of the four. Let's move on to the next one. Is p equals e to the 100 e to the 0.3t a solution? Okay, well, same process. This time we would like to check 100 e to the 0.3t. And so we're going to substitute that into the left-hand side and the right-hand side of the differential equation. Again, the differential equation is this up here. So the left-hand side is going to be dp dt, the right-hand side is 0.3p. And we're just going to take p and substitute it in to both the left and the right-hand side. Okay, so if we replace p with 100 e to the 0.3t, okay, what we wrote is asking us to take the derivative of that, so we're going to get 100 e to the 0.3t, and again by the chain rule, we're going to get a 0.3 that comes down. If you simplify that, 100 times 0.3 is actually 30, and then we've got e to the 0.3t. Okay, what about for the right-hand side? Okay, well there, we're going to take 0.3 and multiply it by p, which is sitting up there. Okay, so what do we get if we take 0.3 times 100? We get 30 again. And what do you think? Do we get the same thing? Yep, those are equal. And so p equals 100 e to the 0.3t is also a solution to the differential equation. Okay, we're using this word solution. That just means it's a formula that happens to satisfy the differential equation. It makes it a true statement algebraically. Okay, and moving on, looks like we've got two more to check here. Okay, what about p equals 200 sine of t? First of all, what does the graph of the sine function look like? It's kind of a wave that bounces up and down. It increases and decreases and increases and decreases. That doesn't appear to fit our slope field very well, okay, because we're getting all positive slopes in our slope field, so I'd probably expect that this is not going to be a solution. Let's see if we can confirm that. Okay, so let's see, what was our formula? 200 sine of t. Right, so this is going to start out the same as it did before. So the left-hand side is going to look like dp dt equals, plug in the p, and we're going to be taking the derivative of 200 sine of t. What do we get when we take that derivative? Well, derivative of sine is cosine, so we're just going to get 200 cosine of t. There's the result of our calculation on the left. And on the right, 0.3p, that's what the right-hand side of our differential equation looked like. We're going to be taking 0.3 and multiplying it by p, which is 200 sine of t. And let's see, 0.3 times 200, that is 60. And what do you think? Did we get the same thing on the left and the right? This time we didn't. These are not equal. And that confirms that 200 sine t is not a solution. Okay, well, we're kind of out of space here, so I'm going to leave part 4 for you, okay, to check p equals 0. This actually is a solution, which I'm going to ask you to confirm algebraically. Okay, and you're welcome to look at my written solutions and see how I did it once you've tried it yourself.